It's not something you learn in AP Physics 2. It's something you'll learn in Physics C. And we also had our magnetism test, so it's not like this is going to be useful anyway. But I did want to make a video on Biot-Savart's law, or Biot-Savart Law, whatever. Biot-Savart Law is kind of the, like, I guess, introduction to, like, or not introduction, but it kind of is a law that kind of shows us how electricity and magnetism are connected, and qualitatively, or I don't know, qualitatively, verbally, I don't know. The verbal, like, but what Biot-Savart Law tells us is that a moving charge can create a magnetic field, right? So electricity, right, through a moving charge, and moving charge is really just current. Moving charge can create a magnetic field. Now, how much magnetic field does it create? Well, if let's say you had a proton or some charge with a speed v, and you want to figure out, I'll do it like this. Why not? With a speed v, and you want to figure out what magnetic field is created at this point P, we'll do it like this. At point P, a distance r away. Let's say you want to figure out what is the magnetic field created here. So what you would do in order, what the equation is, what Biot-Savart Law tells us, is that the magnetic field due to that charge Q is equal to mu naught over 4 pi times Q V cross r hat over r squared, and magnetic field's a vector. So this is a pretty gnarly equation. Let me break this down. Mu naught is magnetic permittivity or permeability. I don't know the name. I kind of forgot, not gonna lie. But it's equal to 4 pi times 10 to the negative 7th some unit. You could figure out what unit is with dimensional analysis. It's just a constant. It's really 4 pi times 10 to the negative 7th, right? Divided by 4 pi. So why did they not just like make a constant, or why did they not just cancel out the 4 pi and set mu naught equal to 10 to the negative 7th? I don't know, but mu naught over 4 pi, it's just 4 pi times 10 to the negative 7th over 4 pi. Okay, so Q we have here, so times Q V cross r hat over r squared. It's proportional to your charge, right? So if you have more charge, it's gonna create a stronger magnetic field at that point P. V, it's proportional to V, so if it's moving faster, it creates a stronger magnetic field. Then you have this cross r hat, right? What does that mean? Well, if you were to take the displacement vector, or like the position vector, r, it's really a position vector, r, you want to take the cross product, right? You want to take the cross product of the velocity cross r hat. So it's not really r, right? You have this over r squared. You want to take the cross product with r hat. That's the unit vector, right? That's the vector. If I were to draw r hat, that's just the vector with magnitude 1 and same direction as the main vector r. That's really just what a unit vector is, right? So the cross product, right? If you were to find the magnitude of a cross product, right? So let's say v cross a vector r hat is really equal to the magnitude of v times the magnitude of r hat, times sine theta, the angle in between. So if we were to look at this angle right here, theta, you're taking sine of that theta. This is just a cross product. You've seen this in the torque equation. It's just that cross product. But the nice thing is well, r hat, the magnitude or the size of r hat is just 1. You're really just multiplying by 1. So you actually end up just getting v sine theta. what that means is if you were to find the magnitude, right? Because this equation, this is a vector like equation, like you're finding the magnitude and direction. If you're just trying to find the magnitude, it's really just B is equal to mu naught over 4 pi times QV sine theta, where theta is the angle between your R, the distance like vector, right? That position vector. It's the angle in between the velocity and R. This is a kind of a simpler way to, or not simpler way, but this is how you find the magnitude, right? If you want to find the direction, you could use this and find the cross product, but you can always use your right hand rule to find the direction. So the right hand rule tells us, right, point your thumb in the direction of the velocity, curl your finger, and that's going to be kind of the direction of point P. So like the magnetic field is like swirling around the charge, and if you look at your fingers, it's going to point into the page right here. That's the direction of the magnetic field. You can also use this one. So you're taking it's V cross R. So V R is kind of like this way, so your magnetic field is into the page, right? So you can use either right hand rule if you know how they work. Okay, so let's say, let me use this equation just because this one you'll see more commonly. Moving charge, what is current? That is moving charge. So that means current can create a magnetic field, because current is really just electrons moving, but you know, we think of positive charge as moving as current. So if we were to think about like the magnetic field due to a current, like a piece of current, like a wire or something, here's how we rewrite it. So we have mu naught over 4 pi times, so current, well, okay, current is really just dq over dt, right? Change in charge over change in time. So that means dq is really equal to I dt, or like the charge, right, at a certain time is just I dt. So I can say that q is really just equal to I times dt times v cross r hat over r squared. Okay, so, and also I forgot to talk about, there's a, hopefully you saw, there's an inverse square relationship with R and the magnetic field. So the farther away you are, the weaker the magnetic field. But what is, now we have I dt times v times dt, right? Velocity is just dx dt, right? Your displacement per time. So v dt is really just dx, or like it's really just like a very small like piece of, okay, I guess I should just substitute this in before I start explaining what it means. Mu naught over 4 pi times I dx. Just for giggles, I'll say dl. You'll see why in a second. Over r squared. So this is Biot-Savart's law for a current element. So if I had a wire, right, this way, this small amount of section I'll say dl, right, this small section is going to create its own magnetic field, like at a point P. So you can use this equation right here if you think about the current going through that small section, the distance from the point you want to solve for. You can use this formula to get the magnetic field there. But hey, guess what? There's a di right here, and dl over here, and that dl is creating magnetic field at point P, and so is this dl, and so is this dl. The entire wire is made up of dl's that are all creating magnetic fields at point P. So what's going to be the total magnetic field at that point P? Well, you're going to have to integrate all of those dl's, and that, so it's really B, like total or whatever, is really just mu naught over 4 pi times the integral of I dl cross r hat over r squared. This is Biot-Savart's formula or law in true form and glory. You really are just integrating here, like it really should be here, but you can pull the constants out, and usually current is a constant too. Like it almost always is. You can pull that out as well. That's Biot-Savart Law. Hopefully this video was a good introduction to how it all works. Thank you for watching.